Sure. Definition: kinetic energy. The energy due to motion of an object. In equation form, kinetic energy equals 1/2 mv squared. You may remember this from a previous tutorial, where m is the mass of the object, v is the velocity of the object. Note that it is squared. The kinetic energy of an object is proportional to the square of its speed, not just the speed. Definition: temperature. Temperature is proportional to the average kinetic energy of the molecules. Remember, kinetic energy is energy of motion. So, as temperature increases, so does molecular motion. The molecules bounce around and vibrate faster. Temperature and kinetic energy. As a gas gains heat energy, this means it has an increase in the average kinetic energy of the molecules. In turn, this means the temperature is increased. On the other hand, if there is a loss of heat energy, this in turn means that there is a decrease in the kinetic energy, which means that the temperature is decreased. Note the relationship between the various quantities. Definition: average kinetic energy. This is the energy due to motion of an object. However, note this is not the same kinetic energy formula that we previously had. For this one, kinetic energy equals 3/2 RT, where R is a constant, a gas constant. One possible value is 8.31 joules per Kelvin moles. The T is the temperature. In this case, it should be in kelvins. From the formula, note that the temperature of an object is proportional to the average kinetic energy of its molecules. As the object heats up, its molecules vibrate at a faster rate. Calculating average kinetic energy. Since temperature is defined as proportional to average kinetic energy, how do you calculate it? Take our previous formula. Remember, R is a constant, and the temperature must be in Kelvin. For an example, let's say we want to find the average kinetic energy of a sample of O2 at 28 degrees Celsius. We're looking for the kinetic energy. We either know or can look up the gas constant, and we'll change our Celsius temperature into Kelvin. We get 301 Kelvin. A little more on this later. Applying this to our formula, substituting, we get an average kinetic energy of 3,752 joules per mole. Average translational kinetic energy. This is related to the temperature by the relationship 3/2 kT, where K is a constant, which is the ratio of the universal gas constant to Avogadro's number. So K is R divided by Avogadro's number, n sub a. Thus, this average translational kinetic energy can be given by 3/2 RT over n sub a. Kelvin, Celsius, and Fahrenheit. There are three commonly used temperature scales. The Kelvin scale, also referred to as the absolute scale, where 0 Kelvin is the temperature at which molecules of an object have no kinetic energy. They stop vibrating. The Celsius scale, based upon the boiling and freezing points of water, very commonly used in science. The Kelvin scale is too. And the Fahrenheit scale, commonly used for weather and commonly used in the US. Definition: Kelvin scale. It's a temperature scale with an absolute zero, meaning temperatures cannot fall below that point. There is no temperature colder than absolute zero. This is needed in gas law calculations because you can't have negative pressures or volumes. So, to get the Kelvin temperature, take a Celsius measurement and add 273. Absolute versus relative scales. For kelvins, 0 Kelvin is the temperature at which molecules of an object have no kinetic energy. This is the absolute rock bottom. When in doubt, for thermodynamics and gas calculations, use kelvins. For the Celsius scale, water freezes at 0 Celsius and boils at 100 Celsius. Nice, neat, round numbers. To convert Celsius, or to find Celsius, take the Kelvin number and subtract 273.15. For the Fahrenheit scale, water freezes at 32 and boils at 212. To find a Fahrenheit measurement, take 9/5 the Celsius measurement and add 32. Temperature scales. Here's a continuum. On one end, molecules are completely still with absolutely no kinetic energy. On the far end, with high temperature, they have great kinetic energy. So on our far end, we have 0 kelvins, water freezing somewhere in between, and on the high end, boiling water, or possibly even hotter. On the far end, we have decreasing temperature to the left, far end of the right, increasing temperature. To the left, we have less kinetic energy, and to the right, we have more kinetic energy. To the left, we have a loss or less heat energy, and to the right, we have more or a gain of heat energy. Note: absolute temperature. The point at which the temperature of an object is absolute zero or 0 Kelvin is theoretical. It cannot actually be measured, and objects cannot actually reach that exact value. You can think of it as a limit or an asymptote. Question: temperature and kinetic energy. If the temperature of an ice cube is -8 Celsius, what's the average kinetic energy in joules of the water molecules? Is it 0 because the water molecules are crystallized as solid ice, so they're not moving? Maybe it's 0 joules because the temperature is below 0 Kelvin. Or maybe it's some number greater than 0 because the temperature is above absolute 0. Look at the information in the question carefully and pick the best answer. It is greater than 0 joules, because the temperature is far greater than absolute 0. -8 Celsius is much greater than absolute 0. In fact, it's around 265 Kelvin. Note: temperature scales. Remember the units. As already mentioned, -8 Celsius is actually 265 Kelvin. So the kinetic energy of that ice is substantially bigger than 0.